Good morning, Los Alamitos AP Physics C students. I have a new webcam. Well, no, it's not a webcam. This is an actual document camera designed for this kind of duty. Instead of just clamping my old webcam in a microphone stand, which is what I've been using for a while. This one actually has a built-in microphone jack, and I have a lavalier microphone I'm wearing around the neck of my shirt here. And soon I may even be able to do the little picture of me in the corner thing, although I don't really see the advantage of that unless you just want to check on the status of my hair loss. So here we go. I posted this. This is what I called the physical pendulum from hell, and I think I got the wrong problem. It certainly had a diagram that looked like that, but this is not a problem from hell. Okay, it is a non-uniform bar, which the physical pendulum from hell was, but this is from, I believe, the 2009 AP, and I don't seem to have a copy of that exam. It's the weirdest darn thing. So, let's go through this one anyway. I don't think this is the physical pendulum from hell because we do not have to integrate to find I. This particular problem says you're allowed to use. They give you I. You have a bar of known mass and length L with a pivot, and you know X, the distance the center of mass is from the pivot, and oh, I see. I see. So we're going to use this term. So express all algebraic answers in terms of I. The setup here is to find I experimentally. Yeah, I don't think this is physical pendulum from hell, but let's just go ahead and finish solving this anyways. Okay, so they are going to want us to write the differential equation. By the way, here's a technique. When you're reading the question, you can make certain marks, okay? So, for example, I might make a mark when it says in terms of. Okay, now I know that my answers have to be in terms of these things. And then when you read the question, underline what they're actually asking you for so you don't answer the wrong thing. Gosh, that's such a great idea. The angle the bar makes with the vertical. So we should probably draw this thing at an angle so we can understand what's happening here. Here's the bar, there's the pivot point. Here's the center of mass of the bar. I know this pen is too big for this application, but there you go. And what's going to happen is there's going to be a force mg acting at the center of mass. That's the whole point of the center of mass. And that's when this thing is pulled to the side a distance or an angle theta. So we're going to need a restoring torque. And the restoring torque is going to be the force times the distance away the force is acting from the pivot point times the sine of the angle between them. These two together make up the lever arm, although sometimes I refer to X as the lever arm. So that's the restoring torque, and restoring torque means it's really going to be in the negative direction. So if we're going to write the differential equation, we're going to start with Newton's. I should use a regular pen instead of these big fat pens, but whatever, we'll get through this. We write that down. That is the torque version of Newton's second law. And now we're going to put in our actual restoring torque. We're going to put in IB because they said we could use that. And then alpha, we're going to write that as d squared theta dt squared. Okay, all we have to do to finish this up is to move IB underneath that other thing. So we should have minus mgx over IB times the sine of theta equals d squared theta dt squared. This could be an answer. Now, in the past, we'd also done an extra step of doing the small angle approximation. I'm saying a lot. That's great. So now I'm going to be self-conscious. We've done the extra approximation, the small angle approximation, but they didn't say anything about small angle approximations yet. So I'm going to leave it in this form because I read down here where it says by applying the small angle approximation, calculate the period. Oh, I shouldn't have underlined this. I'm using underline for what's the damn question. Okay, so calculate the period of the bar's motion. Good. Let's go ahead and do that. I'll go back to the blue pen. Why not? So applying the small angle approximation to this, we're going to replace the restoring torque, or the other thing there, with now we can identify that omega squared is equal to whatever's in front of the variable, not the differential, but the variable without the minus sign. Thus, omega itself is the square root of mgx over ib. Hey, you know what? We already knew this. That is our memorized result from the physical pendulum. Now, if you want to find the period, period is equal to 2 pi over omega, or times the inverse of omega, which means it's going to be 2 pi times the square root of ib over mgx. And so this is the period. I'll have that equal the period, and I'll put a box around this so that the grader can find it very easily. All right. Now, further on, they say, describe the experimental procedure you would use to make the additional measures necessary to determine IB. And if it was me, I'm going to go ahead and I'm going to experimentally measure the period, and from that find IB. So when I do that, this is basically an essay question, but when I do experiments like that, I really want to go ahead and I want to graph something. I want to do a bunch of experiments, but I don't know if, the period is going to stay the same no matter how much I move the thing to the side. So I don't really know how I'm going to get a graph out of this, but I would definitely maybe solve this for IB. So let's go ahead and do that. We would solve this for IB by taking t over 2 pi and squaring that, and also multiplying by mgx. Okay, double check me with the algebra to make sure I did that. I did it all in my head to make sure that's right. So what we would have to do is, knowing x, knowing m, knowing g. So maybe my experimental procedure is to take this thing down, measure the mass on a scale. You can measure x by balancing it or something like that. And then I would swing it a bunch of times, and each time I swung it, I would get the period. Actually, I would swing it multiple times to eliminate error, minimize experimental error. You let it swing not just once and time that, but you let it swing, say, 20 times and time that, and divide the number by 20, and that gets rid of a lot of random fluctuations or timing error. So then I would know what the period is, and I would put that in this equation to find IB. That's probably what I would do. And then it says, now suppose you were not given the location of the center of mass bar, describe an experimental procedure you could use to determine it. Well, one of the experimental procedures, of course, is just to try to take the bar on its side and balance it on some sort of knife point. And as you slide the bar back and forth, when you get to the point where it's balanced, that's where the center of mass is. If you don't want to do that, you could suspend the bar or support the bar either on a pair of scales or on one scale and a pivot point, and use statics, chapter 12, and figure out where the center of mass must be to give you the readings that are on the scale. Hopefully we've done this in class. If not, let me know and we'll do it. We're going to measure some person's center of mass. All right, folks, that's good for today. I do think that I've got the wrong problem here. So this is not the physical pendulum from hell, and I will find the problem that is known as the physical pendulum from hell, and I will bring that to you. Meanwhile, I teased up into the Google Classroom feed the video I made on using calculus to find mass, center of mass, and moment of inertia. Cool.